Hey guys, happy snow day! Here's your lesson for Tuesday. All right, so we're finally starting section 4.5, which is going to bring us to a technique for evaluating indefinite and eventually definite integrals as well. And I've repeatedly told you there is no product rule for integrals, and that's true. So make no mistake, this is not product rule for integrals. All right, but this is one thing we can try if we notice that we're looking at the integral of a product. And because integration is just undifferentiating, I figured we should start with some differentiation first so that you can see where everything is coming from. All right, so here in numbers 1, 2, 3, 4, let's go ahead and differentiate each of the following expressions. Okay, so in this first one, we've got f of x equals x cubed plus 2 squared. So we recognize that at the highest level, we have power rule. So let's use power rule on x cubed plus 2. So we will bring the 2 down in front and then knock the degree down by 1, and then we can't forget chain rule, right? The derivative of the function inside will be 3x squared, right? So we'll just say times 3x squared. And then, of course, we'd probably want to clean that up, right? We could just call that 6x squared times the quantity x cubed plus 2. But actually, this format on top is fine for now for this lesson. All right, so moving on to number 2. All right, well, okay, at the highest level, we have sine of something. And the derivative of sine something is cosine of that something. But now the function inside has its own derivative, and the derivative of the something inside is 2x. So we'll chain on a 2x, and we'll tidy this up a little bit. And that's done. Moving on to number 3. Okay, an exponential, not a big deal though. We know that the derivative of any exponential is itself, so we will write down the original exponential and then chain on the derivative of the inner function, which is the expression in the exponent right up there. And the derivative of the expression in the exponent is, let's see, 2t minus 3. And yep, that's sort of as good as it gets. Number 4. Okay, we've got a natural log, and we know that the derivative of natural log anything is going to be 1 over that anything. But then the function inside has its own derivative too, and that derivative is 6x squared. So at the end of the day, it might be more convenient for us to write this as 6x squared over 2x cubed. And of course, right, we would simplify that, but again, for the purposes of illustration, I'm going to leave it like that for now. All right, and so now, when we sort of come back out and look at the big picture here, we know some things, right? We've got 4 derivatives, right? And so if we know that each of those expressions are somebody's derivative, we know they're antiderivatives. And so that's exactly what I'm getting at in the thus part here, right? Because the expressions in blue are the derivatives of the functions listed in numbers 1 through 4, the functions listed in 1 through 4 are the antiderivatives of the expressions in blue. And that's exactly what I've given you right down here. So let's take a look at this first one here. All right, this first expression here, right, this first integral, right? So notice how this relates to the first problem that we did, right? We see a function and its derivative outside here. The 2, right, that came from the application of the power rule. But the most important thing is the idea that this is a function and that this piece came from applying chain rule, right? And so, right, we know where we started, so we know what the antiderivative is here, right? The antiderivative of this is going to be x cubed plus 2 squared plus c. Always plus c, right? Let's move on to number 2. So again, we see this pattern of an inside function and then what looks like it could be its derivative hanging around nearby. And so we recognize that we're looking at the integral of a product because we used chain rule. All right, and so of course we know what this will undifferentiate to, right? This is just going to go to sine x squared plus c. All right, moving on to number 3. All right, again, we're looking at the integral of a product, right, which we know we can't handle, but not all is lost because we recognize that we must have gotten here through an application of the chain rule. Because if I consider this little guy up here my function, I look and I see its derivative sitting right there, chained on, right? So this would undifferentiate to e to the t squared minus 3t plus c. And last but not least, right, this is a little trickier because we'd probably be looking at this in simplified form, but for right now, it's good enough. Now notice, I see a function, what looks like it could be the sort of parent function, I guess, on the bottom, actually, and the expression on top looks like it could be the derivative of that function on the bottom, right? And so then, well, I know that when I'm looking at something to the tune of, you know, a derivative over itself, right, that's a natural log, right? Because the derivative of natural log is 1 over itself and then chain rule, right? So we know that this undifferentiates to the natural log of 2x cubed plus c. And that's going to be the whole idea behind u substitution, is looking for the pattern of function derivative somewhere nearby. All right, so let's move on to the next page. Okay, so these are going to be some relatively simple examples of the chain rule, all right, in which we pretty clearly see the function derivative pattern, all right, and I'm going to step you through this. I mean, you might be able to do these, you know, just by thinking a little bit, and sometimes taking that thinking step will help tremendously. You can save yourself a lot of time, but I'm going to take you through all the mechanics because we're going to have to use those later. All right, so let's take a look at this first example. All right, so just examining my integrand, I'm going to start looking for a pattern of function and derivative. And I notice that if I consider x to the 4th my function, I see its derivative right there. Notice, just x to the 4th, not sine x to the 4th. I don't see a cosine anything hanging around. So because I just see the derivative of x to the 4th, I'm going to say, you know what? I'm going to call that u. X to the 4th, you are now u. All right, and I saw its derivative as well. All right, so in this next step, we acknowledge that the derivative of function u with respect to x, right, because it's a function of x, is exactly what I see in red, 4x cubed. Okay, so now we are going to try to transform this integrand from an expression that uses x's to an expression that uses u's. So let's just start rewriting. I'm going to write my integral symbol. All right, now, instead of writing sine x to the fourth, I'm going to write sine u, because apparently they're equal the way I've defined it. So I will write sine of u. Now, if I'm going to be writing the sine of u, I should probably be integrating with respect to u. All right. So with a little bit of algebra, all right, and we're going to use algebra on this part here. All right, with a little bit of algebra, we can see that, right, by multiplying both sides by du dx, I can get that du is equal to 4x cubed times dx. That was just an algebra step, nothing fancy there. All right, but now look at what I can do here. All right, apparently, just by going back here and writing du, guess what? Du scoops up a number of things, doesn't it, right? By writing du, I've all of a sudden taken care of 4x cubed and dx. Since du is equivalent to 4x cubed and dx, right? I took care of the sine part by writing sine, and I took care of the x to the fourth part by writing u. So everybody in the original integrand is accounted for. And now look at this expression that we actually have to integrate. It is so easy. All right, so let's do this. All right, sine u will undifferentiate to, let's see, that would have to be negative cosine u plus c. And then a good last step is to back substitute, right? We should probably, leave our final answer in terms of x, not in terms of u. So let's just do that, right? So instead of negative cosine u, we'll say negative cosine of x to the fourth plus c. And you can always be confident that you have integrated correctly if you differentiate and you wind up back where you started. Not too bad, right? All right, let's move on to number 2. All right, and so again, everything is going to hinge on us being able to recognize a pattern of a function and its derivative sitting somewhere, right? And so I take a look at the expression and, well, let's see. If somebody's going to be a function and somebody's got to be a derivative, I would say that the higher power has to be the function, right? So this whole thing, right? There's no reason not to throw the plus 1 in there, right? And then this guy hanging around out here would be its derivative. So this is great. So whatever you can identify as parent function, that's going to be your u. So let's let u equal x cubed plus 1, and then we'll acknowledge I see u's derivative hanging around too, right? The derivative of function u with respect to x is 3x squared. Yay! All right, let's just start rewriting our integral. We'll see what we need to get. All right, I call this the bookkeeping method, by the way, because it's just me keeping track, making sure that everybody in my integrand, my original integrand, gets accounted for. All right, so we'll write our integral. All right, and instead of writing root x cubed plus 1, I can just write root u. So guess what? That took care of the radical, and that took care of this x cubed plus 1. So I still have to get a 3x squared in there and a dx. That's got to get in there somehow. And then, of course, that's going to all go back to this, right? And just doing a little bit of algebra on this, right? Because with just a little bit of algebra, I see that du is equivalent to 3x squared times dx. And so now if I just write du, I scoop up both of those pieces, right? So just writing du takes care of my 3x squared and my dx. And we are done. right? And now this is a relatively simple integral here, right? We'll just rewrite this. This is really u to the 1/2 du. And then we just reverse power rule, right? So we'll say, okay, that's going to be u to the 3/2 over 3/2. So I'm going to say times 2/3 plus c. And then the last step, just for good manners, will be to back substitute so that our expression is in terms of x's. All right, and that'll give us, let's see, u was x cubed plus 1. That was to the 3/2 plus c, and we are just going to leave it. All right, example 3. Okay, so again, we're going to have to make a choice, right? So first of all, we want to decide, do I see a function and its derivative hanging around somewhere? And I sure do, right? I'm seeing this x squared and this 2x, and so I would say that, well, the 2x, you've got to be the derivative. So what is my function? Well, if I'm going to say x squared, I might as well say x squared plus 1. All right, don't worry about x squared plus 1 squared. We'll handle the squaring part. We'll bring that back in. All right, but for now, if 2x is going to be my derivative, my function can be no more complicated than x squared plus 1. All right, so let's write down those definitions that we chose. We said, okay, u is x squared plus 1. The derivative of function u with respect to x is therefore 2x. And let's start rewriting. So instead of x squared plus 1 squared, right, I can just write u squared. All right, so that takes care of my x squared plus 1. That takes care of the squared part. See, we got everybody. It's all good. Right, and then I still need to get a 2x in there and a dx in there, and then, of course, just pretty much like clockwork here, that's going to hinge on this little definition right here, right? And we notice how conveniently it turns out that du is equivalent to writing 2x times dx, right? Just with a little bit of multiplication on both sides. So by simply putting du right in here, I take care of my 2x, I take care of my dx, and everybody's been represented in our new integrand below. And then look at this. I mean, it doesn't get simpler, right? This is just reverse power rule. So this is going to be u cubed over 3 plus c. And then for good math manners, we will just back substitute with x's instead of u. So u was the quantity x squared plus 1 cubed over 3 plus c, and that's a wrap. Now, of course, it doesn't always work out so nice and peachy keen, right? But if you get this much, you get the general idea, and the rest of it's not too terribly different. All right, so an example of when it might not work out so nicely is on the next page. So let's take a look. All right, so, all right, if we take a look at example 4, we notice not everything is perfect. In fact, this problem is exactly like the last one with one key difference, right? In example 3, we had this 2 hanging around right in front so that we were like, oh, sure, x squared plus 1, you're my function, 2x, you're my derivative, and life was good. But that is not the case. Right? Instead, we see the function, but we don't really see its derivative. I mean, we're like, well, x, you were close, but it's not quite right. All right, and the solution here is that it doesn't matter, right? The derivative of x squared plus 1 is 2x. We have x. That's a difference of a scalar multiple, right? A 2 versus a 1. And we know that apparently in calculus, scalar multiples are not a big deal, right? So the important thing is that that x hanging out in front is of the right order to be the derivative, right? If we differentiate a squared term, we should get a linear term. So that's really what we care about, right? We care about that the derivative of x squared plus 1 is going to be something x. So we're still in business. And watch how much of the math, right, that the u substitution takes care of for us. Sometimes you don't know where these are going. You just start doing them and they work themselves out. I love that. So let's get going. All right. We'll still let u equal x squared plus 1 because it's of the highest power. In this case, the derivative of u with respect to x is 2x. Not exactly what we want, but okay. All right. And again, my recommendation at this point, just start rewriting. All right. So let's get it going. So this will be the integral of, well, we'll have u squared. All right. So that takes care of this guy and the squared part. Good. And now we still need to replace x and dx. So, oh, guess what? It all comes back to this. And we're going to do a little bit of algebra with this. And watch how nicely this works out here. All right, so with just a little bit of algebra, I get that du must equal 2x times dx. However, I don't need to account for a 2x dx. I just need to get an x dx in there. Well, guess how we can get that? Just divide both sides by 2, right? So du over 2 is going to give you your x dx. All right. So apparently by writing now not just du, but du over 2, that's equivalent to x dx, and that's going to get everybody in without any extras. All right, so let's write that. Whoops. Pen. Haha. Du over 2. And exactly as it says over here, du over 2 is equal to x dx. Done and done. And now, okay, this integral requires a little bit more work, right? Because we'll pull out a scalar multiple of 1/2 first, but whatevs. Still easy. All right, and so this will integrate to 1/2 u cubed over 3 plus c. And then we'll just tidy it up. We'll back substitute. Right, 1/2 times 1/3 is going to be 1/6. Instead of u cubed, I will write x squared plus 1 cubed plus c. Done and done. So the bottom line is that a difference of a scalar multiple is never a big idea, and the math takes care of it on its own half the time. All right, let's give example 5 a shot. All right, so in example 5, we don't see exactly what we want again, right? We recognize that this t to the 4th plus 5 is in really good shape to be our function, and t cubed, well, it's not the derivative of t to the 4th plus 5, but you know what? We don't care. We just care that it's of the right order to be the derivative of t to the 4th plus 5, right? Derivative of something to the 4th should be something to the 3rd, and we're in business. So let's get started. We will call our function t to the 4th plus 5, and then we'll go get its derivative, right, that we see, or at least we see something close to it, right? The derivative of u with respect to x will be 4t cubed. And so let's start rewriting, and we'll see what we need. Okay, we'll see what sort of algebra and sorcery we need to do to make this work. All right, so the integral of, well, instead of writing the square root of t to the 4th plus 5, I can write the square root of u. And so that takes care of the square root part, and that takes care of the t to the fourth plus 5. So now we just got to find a way to get the t cubed represented and the dt represented. And I made a whoopsie here because I wrote dx, and that's incredibly sloppy of me, right? That should be dt. Okay. Learn your lesson? Good. All right. Yeah, because we need to account for the t cubed and the dt. All right, so let's do some algebra. Right, with a little bit of multiplication, we can see that du is equal to 4t cubed times dt. And now I'm like, oh no, I only need to replace t cubed and dt. I don't need that 4. All right, well then let's divide it out, right? Let's divide both sides by 4. And oh, look, there it is. du over 4 is exactly equal to t cubed times dt. So let's write it. And then again, all right, putting things over 4, that's just multiplying by 1/4. So we will pull out that scalar multiple and proceed as usual. And of course, it's going to be much easier for us to think of that root u as u to the 1/2. And then we just chug along. All right, so let's reverse power rule. U to the 1/2 will become u to the 3/2 over 3/2. So I'm going to say times 2/3 plus c, and then we tidy up and back substitute. Okay, so let's see, 2 over 4 times 3, that's 2 over 12, so we'll call that 1/6. And then u to the 3/2 is going to be t to the 4th plus 5 to the 3/2 plus c, and that's good enough. Good job, everybody. All right, example 6. Okay, looks slightly more intimidating. I don't know, it's a fraction. Fractions always look kind of more imposing, right? And so, right, your first red flag should be, oh my god, we don't have quotient rule for integrals, right? So no. All right, right now, the way we handle that is, right, if we don't have a single term denominator, is use substitution. So let's start looking for a function and maybe its derivative, right? Well, I see the x to the 4th and the x cubed. That's a red flag right there, right? So I could make 1 plus x to the 4th my function, right? No reason not to include the 1, right? And then x cubed, you could be its derivative, or at least something close to it. All right, so let's start writing. U, we said, will be 1 plus x to the 4th. Then its derivative would technically be 4x cubed. All right, so let's start rewriting. All right, well, let's not worry about the numerator just yet. That'll all fall into place. But I know that instead of writing 1 plus x to the 4th squared, I can write u squared. And then that takes care of this much and the squaring as well. So that's accounted for. Good. All right, well now we just need to get an x cubed and a dx in there. All right, well, you know how we're going to do it, right? We're going to come over here, multiply both sides by dx, and then we're like, oh man, I don't need 4x cubed dx, I just need x cubed dx, right? There's no reason that dx can't go in the numerator. Not a big deal. And we're like, oh, cool, well, I can get exactly that if I just divide both sides by 4. Perfect. So, by writing du over 4, I'll scoop up the x cubed and the dx. And you know what? I'm just going to put it right out here, right? Putting it next to the fraction bar is as good as putting it in the numerator, okay? So now that I don't get confused, I'm just going to put a 1 up there. Fine. All right, so let's rewrite this. All right, that whole over 4 thing, I'm just going to think of that as a scalar multiple of 1/4. Now, du over u squared, that's really going to be u to the negative 2, right, times du. And then, oh, look, reverse power rule. Thrilling. All right, so let's do it. 1/4, we will bump the degree up by 1 and put it over that exponent, plus c. All right, and so now we'll tidy it up. So, okay, now be careful here, right? That over -1, that's just going to change the sign, right? So that'll make it a -1/4. And then the fact that it's u to the -1, we'll just send it down here as u to the +1. And then we'll just make sure that we keep everything in terms of x. Good math manners. Now the question is, what the heck was u? 1 plus x to the 4th. Alrighty. 1 plus x to the 4th plus c. Done. Beautiful. So here's the good news. Most of the u substitution problems that you see are going to work just like that. So if you can do these first 6 examples, you can do most integration. In fact, pretty much all the integration that we're going to do for the remainder of the year. All right? But you know it can't be. All right? It doesn't always work out that way. Okay? However, the fix is not that bad, I promise you. Okay? And so this is right, because this is going to be all we have. This is really the only integration technique that we'll learn that's not an integration rule. Like, oh, sine integrates to this, right? This is a technique, okay? This is a method. This is it. So if you can't do it with a u sub, you know, at least for AB calculus, we can't do it. So this has got to get us through everything, all right? Including times when you don't see the function derivative pattern. All right, so let's talk. All right, I'm looking at example 7, and I'm not loving it, right? I mean, okay, so this 2 minus x, if that's my function, well, the derivative of that expression inside is -1, and that's not what I see out there. All right, so that's not it. And if I let this be my function, well, the derivative of x plus 1 is just x, and I don't see that either, right? So we feel like we're at an impasse, but of course we are not. Teddy, that's not no solution. All right, so we're going to proceed as normal. And in general, I recommend that you choose u so that the thing that bothers you goes away, all right? You know, so that you sort of account for the more complicated part of the problem. All right, so I'm going to let u be the 2 minus x because that's under a radical, all right? And I would rather, you know, the radical is going to be more difficult than the other part. All right, so let's go for that. Alrighty, let's do u equals 2 minus x. Okay? And we're going to do the exact same thing. Okay, so we're going to say, well, the derivative of u with respect to x is -1. Cool. All right. And so again, this, you know, just start rewriting, see what you need. We'll come back and get stuff. All right. So I'm going to start rewriting my integrand. All right. I will write root u. Cool. All right. That takes care of the radical and the stuff inside. And I'm like, all right, well, I've got to replace the dx with something. All right, and again, I can just do that right here, right? If I multiply both sides by dx, I get that du equals -dx. Therefore, -du must equal dx. So if I want to scoop up the dx, I'm just going to write -du. Just drop it in. We'll clean it all up later. Great, you're taken care of. And now I'm like, x plus 1. There's nothing for you. But there is. We have a relationship between u and x. So all we're going to do, all right, because we don't see the function derivative pattern, is we're going to take our initial definition of u one step further. All right, so with just a little bit of algebra over here, right? Well, let me subtract 2 from both sides. U minus 2 equals negative x. Therefore, right, if the opposite of x is u minus 2, then x equals 2 minus u. And there we go. Now I've got something that I can replace x with. So let's do that. In our integrand, instead of writing x, I'm going to write 2 minus u, and then we just need the plus 1. Bam. Okay, now this, right, this is not pretty yet. We will clean it up. We will do much cleaning. All right, so let's see. Let's move the negative right here. Let's move that out front. Get it out of the way. All right, and now 2 minus u plus 1. Let's just call that 3 minus u, right? So we're just going to simplify this a little bit. Okay, we're going to call that 3 minus u. Alrighty. And then, all we need to write now is root u and du, and we'll be all squared away. Whoops. Just going to erase that there. All right, so let's just add in the root u and the du. All right, and at first, this doesn't look much better because we still have the integral of a product, but it doesn't have to be, right? Because we can distribute. We can deal with this. So let's do that. All righty. So I'm going to have negative integral. And now 3 times root u is going to be 3 root u. I'm going to say 3 u to the 1/2. And then u times root u, that's u times u to the 1/2. So that's u to the 3/2. And then that's all times du. And now we're good to go. All right, so we'll keep the negative. We'll keep the negative out in front. All right, and then this will integrate to 3 u to the 3/2 over 3/2, which is times 2/3, right? And then u to the 3/2 will integrate to u to the 5/2 over 5/2, which is times 2/5. Alrighty, and then we'll throw the plus c on there. Okay, so we'll really just tidy it up. All right, I'm going to do a couple things. I'm going to simplify my fractions. I'm going to distribute the negative out in front here. All right, and I'm going to back substitute my u's for x's. Okay, so let's see. I'm going to distribute the negative, so I'll have negative. These cancel out, so negative 2 instead of u. I shall write, what was it, 2 minus x to the 3/2. Distributing the negative again, I'm going to get plus. All right, well, the 2/5, that does not reduce. And then instead of u, that's again 2 minus x to the 5/2, and then plus c, and look at how fancy we are right here. Looks complicated, is not complicated, right? I mean, it is what it is. All right, so the moral of the story is sometimes, right, you need to go back and algebra with your original definition of u, just like you algebraed with your du dx. All right, so let's try one more, and then we're going to call it a day because, oh my goodness, that is just enough u substitution for quite a while, at least until next class. All right, example 8, coming for you. All right, here we go. All right, so again, you recognize this is a problem, all right, because if I let u equal 2x minus 1, I don't see its derivative up top, right? And if I let u equal x, I'm in the same position. All right, so you know what? We're gonna do like we would normally do. I'm inclined to choose u as 2x minus 1 because it's under the radical. Looking for grouping mechanisms is helpful. All right, and so let's just go to work. All right, so the derivative of u with respect to x is 2. Yay. All right, and we'll just start rewriting. We will see what we need. We'll go back and get it. All right, so my integral. I do not have anything for x right now, so I'll come back to it. But I know that at least in my denominator, I can put a root u. That takes care of my radical. That takes care of this as well. I'm like, all right, I don't have anything for x. I could probably get something for dx really easily, right? If du is 2 times dx, then dx must be du over 2. Right? Just divide both sides by 2. Bam, bam. That's what I want. That is exactly equal to dx. So by writing du over 2, I take care of u. All right, so now we just got to go get the x. And not all is lost because we know that all we need to do is look back to this definition right here. All right, so let's add 1 to both sides. And then we'll divide both sides by 2, right? So therefore, x is equal to u plus 1 over 2. All right, so again, I'm just going to write that off to the right so that I don't end up with this like nasty looking expression. So I'm just going to pop a 1 right here. And then instead of writing times x, I'm going to say times u plus 1 over 2. And that was exactly equivalent to x. So now all my little ducks are in a row. And then again, all right, so we got to clean some stuff up. Not a big deal. All right, I've got a times 1/2 here and a times 1/2 here, right? Because it's over 2 twice. So really, that's going to be a 1/4 that comes outside. And now I'm really looking at something like this. U plus 1 in the numerator over root u times du. And everybody's accounted for. And look at what we have here. We have our favorite thing. We have an STD. So let's use that. All right, because we're like, oh no, we still have a quotient. No, we don't. We can fix it. All right, so 1/4 u over root u. Well, that's u to the 1 over u to the 1/2. So that just leaves us with u to the 1/2. And then 1 over root u, that's u to the negative 1/2. And then all of that times du, and then we integrate. So 1/4, you're along for the ride. And let's see, u to the 1/2 will integrate to u to the 3/2, right? I think like we've got this memorized by now. U to the 3/2 over 3/2, so times 2/3. All right, and then plus u to the negative 1/2 will integrate to u to the positive 1/2 divided by that 1/2, so times 2. All right, and technically I should have all of this in parentheses right here, and then my plus c. Actually, it doesn't matter where you put the plus c. All right, so now all we got to do is clean this up. All right, so I'm going to clean this up right down here, actually. So we'll have 1/4 times 2/3. Geez, what was u? 2x minus 1? 2x minus 1 to the 3/2 plus 2 times 2x minus 1 to the 1/2 plus c. You could go ahead and distribute in the 1/4 if you want. You could leave it. The world is your oyster. Right is right, as long as you've back substituted. All right, so Thanks for sticking with me. I know this was a lot at once, but I just wanted to make sure that you had sufficient examples and practice. Khan Academy has some good additional examples as well. However, they get into some different types of function classes. You've got some homework posted due for Thursday. Email me if you have questions. Thanks.